Okay, so section 2 has to do with oxidation numbers. So don't let the word oxidation number be strange to you. It's essentially charges, okay? Essentially charges, okay? So in order to indicate how the electrons are distributed between the bonded atoms, what we do is we're going to use the idea of electronegativity, but we're not going to spend time, try to figure out, what kind of bond and stuff like that. We're just going to work at what the charges are, or the oxidation states between the different atoms or ions that are making up the formula. Okay, so that's what we're going to be doing. Okay, first of all, specific rules are used to assign oxidation numbers. So we have some rules that we follow so that we can, and by the way, oxidation numbers, we are not giving what the total charge is. We're talking about basically what is the charge on each atom. That's why we use the word oxidation number for like the charge on each atom. Okay? Now, as a general rule, when it comes to assigning these oxidation numbers, if they share electrons, the more negative element, whether it's the higher electronegativity, is where the electron's that's being shared is going to spend more of its time. Okay? We kind of talked about that in a previous chapter, but just want to make sure that you know that. Okay, so first of all, here's rule number 1, the easy rule. Okay? Atoms in a pure element, in other words, they're not combined with any other element, have an oxidation number of 0. Okay? Have an oxidation number of 0. Now, let me write something up here. Like, for instance, if I have oxygen molecule, which is O2, it's an oxygen's bonded just to the same kind of element. So each of these, it has an oxidation number of 0. That's what we're saying. Okay. It's only when it's bonded to a different element that has a different electronegativity where they will have a different oxidation number. Okay, now the more electronegative element in a binary compound is going to get the negative charge, and the less electronegative one is going to be assigned the positive one. Okay, so for instance, if we have a compound, let's say hydrogen chloride. Now, if I take my periodic table, look on the back side, which one of these is the more electronegative and which one is the less electronegative? Okay, so with your periodic table, you have to look on the back side. Which one is more electronegative, which one is less?
Chlorine's more electronegative.
Okay, chlorine is more, so that's going to be the negative one. Hydrogen then is going to be the positive one. So this is negative, this one's positive, and their total charge, not the oxidation numbers, the total charge has to add up to 0. So what do you suppose each one's got to be? What two numbers would add up to 0? What's the easiest two?
1 and negative 1.
Yeah, let's use like a positive 1 and a negative 1. When I add those together, this positive 1 and added to that negative 1 is going to add up to 0. So that's how we know that hydrogen is going to be +1 and chlorine is going to be -1. Now, I had you kind of guess what number to put in there. We're going to have to have some rules so you don't have to just be guessing at that. Now, fluorine is always going to be a -1. What do we know about fluorine electronegativity? What did we learn about this earlier, about fluorine?
It has the highest electronegativity.
It has the highest electronegativity. So there's nothing that's going to make it ever be positive, because it's the highest electronegative. So fluorine will always be -1. So if you have, now the only exception would be if I had this, right? Because then it's not bonded to anything else. So then it's still going to be 0. But if I have, let's say, hydrogen fluoride, in this case, we just read in that rule, that one's always -1, always -1. So that means hydrogen has to be what? So that the sum of their oxidation numbers will add up to 0. So hydrogen has to be what? +1, right. Okay, it'll have to be a +1, so it'll add up to 0. So that fact of adding up to 0 we'll use a lot to make sure that we've done it correctly. So fluorine, so rule, kind of like, rule number 1 was every element that's not bonded to anything else is always 0. This rule number 3, fluorine is always -1. Rule number 4, and this should match up with your chart that you're memorizing for your on your ion quiz. Okay, oxygen, another element that appears very often, so we like to have rules for that. Oxygen's oxidation number is going to be -2 almost all the time, unless it's a peroxide. Okay, unless it's a peroxide, or it is bonded with a halogen. Okay, so those are like the 2 exceptions to that. So most of the time, and if you look on your common ion table, oxygen, what does it have beside oxide? -2, right? That's -2. Now, if you look on your periodic table above oxygen, it gives you what the 2 possibilities are, right? -2, -1. The one at the front usually is the one that it does most often. So if you look on here on the front side, not the electronegativity side, but the front side, you can see above oxygen it has -2 and -1. Those are the 2 possibilities. So it's either -2, which it is maybe like 90% of the time, or it's going to be a peroxide. And what is the oxidation number on each peroxide? Okay, so oxide has a oxidation number of -2. If it's peroxide, which is O2, what's the overall charge on O2 from your, let me write this with something else so that you can see it's with something else. I guess I'm getting down below what we can see on the board. So we'll put O2 up here. O -2. Okay, then we have peroxide, which I said like this. Okay, peroxide, O2. What's its charge from the table? Okay, if you have your ion table, what's peroxide? Middle column on the bottom. I'll tell you where to look. Okay, so this whole thing is -2 charge. So that means that each oxygen, because remember oxidation numbers, we're talking about each atom. So then what would be the oxidation number for each atom of oxygen then? If 2 of them together is -2, each one has to be what? -1 then, right? So this one is -2 when it's an oxide. If it's a peroxide, it is -1 is its oxidation number. Remember, oxidation number, I keep saying this over and over again, is for each atom. This is the total charge for both of them together. Both of them together is a -2, but each one means each one has to be a -1. Okay, and then they have OF2. We kind of have rules on this one. What was rule number 3? Fluorine's always -1. So we know this one's -1, right? There's two of them, that's -2, so then what does oxygen have to be? +2, right? Is that one of the things on my periodic table that I have here? Is +2 listed? Or does yours have a +2 on yours? Mine doesn't. Mine just has -2 and -1. So +2 is not very common. So it didn't even make it onto my chart. Okay? Okay, so oxygen's almost always going to be -2. Fluorine is always -1. Hydrogen, another element that happens quite often. Remember we were talking about all the acids yesterday. Hydrogen is almost always going to be +1. So for instance, in H2O, as an example there, in water, here's oxygen. We've already covered that one. What oxidation number does oxygen have most of the time? -2, okay? So that means each hydrogen is going to have what oxidation number so that it'll add up to 0? It's going to have to be, together it's +2.
7.
Okay, so each one then is going to have an oxidation number of +1. That matches what it says in our rule here. Hydrogen's almost always +1. The only time that it's not going to be a +1 is if it's combined, as it says, with, well, and when actually hydrogen is the more electronegative. That means it's bonded to a metal. So, like for instance, if I had lithium like that, and I look up the electronegativity for hydrogen, and I think that we've looked at that one so often, I know it's 2.2. And lithium is right underneath it is 0.98. So since this one is less electronegative, this one has to be the positive one. Hydrogen can't be the positive one because it's more electronegative. So in this case, now, what charge do all the elements in the first column of our periodic table have? What do they all have? +1, right? So all of in the first column are +1. That means hydrogen has to be -1. Now, what do we call hydrogen when it's at the end of a formula like this instead of in the front? We call it a hydride. Remember the elements at the end in an "ide" if it's binary? So this one, instead of hydrogen, we change it to hydride. Hydride. Okay? And then we already talked about this already, but now here's the official rule. The algebraic sum of the oxidation numbers of all the elements in a neutral compound is equal to 0. Okay? If it's a polyatomic ion, it has to add up to the charge of the ion. Like for instance, if I was doing it for, let's say, sulfate, which we know has an overall charge of -2, then it has to add up to -2. Now, just to take a little practice at this with what we already know, do we have any rule for sulfur, let's say it that way, so far? Nope, don't have any rule for sulfur. So let's go with one of them we have a rule for. Oxygen is almost always what?
-2.
-2, okay? So if this is a -2, and there's 4 of those, I'll write it this time underneath it, then the total charge is -8, right? If each oxygen's -2 and there's 4 of them, that gives us a charge of -8. What does sulfur need to be so that it will add up to the charge on the ion? It needs to add up to -2. What does that number have to be?
6.
6, okay? So +6. Okay, that's the oxidation number for sulfur. Now, again, let's look at our periodic table and look right above sulfur. Is 6 one of the ones that it can be? Yeah, it is. So in other words, that's probably, we're kind of can sort of safely assume we've done it correctly, because we got a number that actually is on our chart, okay? But it doesn't always work, does it? Remember we said that for hydrogen, well, I guess hydrogen, does yours say +1, -1 on the top of it? Okay, +1's what it does most of the time, -1 was like in this example right here. So here, you know, we found one. Where was one of them that we said wasn't on there? We did one of those. Oh, oxygen was, over here was +2. That's not on my list, okay? Did you get a big enough wad? Not that big? When you have to chew big, then it must be big, I guess. That's what I always figured. Okay, rule number 7. The algebraic sum of the oxidation numbers of all the atoms in a polyatomic ion, that's what we had here. Sulfate is a polyatomic ion, has to equal to its charge. We already did that, okay? We already did one like that. Now, as it says, although rules 1 through 7 apply to covalently bonded atoms, oxidation numbers can be assigned to atoms in an ionic compound. Okay? So what we've been doing here is for molecules, covalently bonded molecules. But you can actually do it, as it says here, for ionic compounds as well. You can do it for ionic compounds as well. And if you have a monatomic ion, it has an oxidation number that's equal to its charge. Like, so if you look on your common ion and you find, let's say, calcium. Calcium is 2+, so then what would be the oxidation number for calcium?
-2.
Well, it would be just equal to it. It's just +2. It's not adding up to anything yet, okay? So it'd be +2. So that's what they're saying there on that. We'll skip that. So let's do a little bit of practice here. So first of all, well, we have UF6. Okay, UF6. So let's look at the rules. Okay, they say it's +6 and -1, but why would that be true? So which one of those two, uranium or fluorine, do we have a rule for?
Fluorine.
Fluorine, and fluorine said it's always -1. Okay, so I have -1, and there's 6 of them, so that would be a total charge of -6. And we had a rule that says all of these need to add up to what? 0. Okay, has to add up to 0. So what would I add to a -6 to get 0?
6.
+6, okay? So that's why uranium's +6 and fluorine's oxidation number is -1. Okay, what about that one? Okay, now this one has 3 parts. Okay, 3 parts to it. We have a hydrogen, a sulfur, and an oxygen. Okay, just a reminder, oxidation state is for each atom. Okay, in H2SO4, which of those do we have rules for?
Oxygen.
Okay, we have a rule for oxygen. Oxygen oxidation number is almost always what?
-2.
-2. We have 4 of them, so that's going to add up to a -8. Let's put that up here. Okay, you said each one's a -2. There are 4 of those, so that's a -8 altogether. Then we have the one for sulfur and the one for hydrogen. Okay, what's hydrogen? Do we know one? Which of those 2 do we know? Hydrogen or sulfur? We have a rule for hydrogen, and it's almost always what? +1. So each one's +1. So then 2 of those would be +2. So what does that have to be? Oh, by the way, what does this have to add up to?
0.
Has to add up to 0 because it's not a polyatomic ion. So what does that have to be there?
Positive 6.
It'd have to be a 6, right, to add up. And then again, you can check it on here. Yes, sulfur is 6 is one of those, so we did do it correctly. Let's do one that's a polyatomic ion. Okay, so here we have chlorate, ClO3, and its overall charge is a 1 negative. Do we have which of these do we have rules for? Oxygen, and it's almost always -2. Okay, there's 3 of them, so that would be a -6. And what does it need to add up to?
0.
It has to add up to its charge, because this is not, this is an ion, polyatomic ion. This one has to add up to -1. So what does this need to be here so that it'll add up to -1?
6.
5.
Does it have to be a 5, positive 5? Positive 5, -6 is -1. So this oxidation number is a positive 5 for chlorine. Now, just before we answer your question, is positive 5 one of the things on my chart?
Yes.
Yes, it is. The choices are 1, -1, 7, 5, or positive 7, positive 5, positive 3. Okay, what was your question?
How can you tell if it's like a polyatomic ion and it means like
Because up here they put a negative after it.
oh,
Okay. On the top 2 they didn't, so we knew it was a whole molecule, had to add up to 0. But if they put a charge at the end of it, that means that's what it has to add up to.
Okay.
Okay, good question. Good question. Okay, now many nonmetals have multiple ones, and we've been talking about that. So far we've had oxygen that could be -2 or +2 or even -1 in peroxide. We had sulfur be +6. I guess here we had another +6 over there. So do you notice that? So these over here will have more oxidation numbers than just a single one. All of these over here have just single ones. These may have more than one as well. But so here's a list of what's the different common ones that you could have. Okay, now taking what we've learned here and using the stock naming system, that's the one with the Roman numerals. The stock system is actually based on the oxidation numbers. Since you didn't know about oxidation numbers when we first talked about the stock naming system, we just kind of skipped over it. And it can be used as an alternative to the prefix system for naming binary molecular compounds. That's where we use Roman numerals. And the Roman numeral is actually the oxidation number. So if you figure out an oxidation number for a cation, then you can just use that for the Roman numeral. That's basically what it's for. So here is just a list of elements, or compounds I should say, and the 2 different ways that we could name it. Okay? The first one, if I use the prefixes, remember that if the first element is just a single one, I don't have to use a prefix for the first name. Only if there's more than one do I have to say something about that. So the first one's just going to be phosphorus, and then the second one is going to be chloride, and then there's 3 of them, so it'd be phosphorus trichloride. So I think the first column probably is pretty easy with the prefixes, right? Next one is going to be phosphorus pentachloride. The third one has more than one N, so we have to say how many. We're going to say di. So dinitrogen monoxide. Next one is, I don't have to have a prefix because there's only one N in NO. So it's nitrogen monoxide. Notice there's always a prefix on the second name, only a prefix on the first name if there's more than one. That's kind of the general rule. Now, the stock naming system is a little harder on these, isn't it? I have to figure out what the oxidation number is for phosphorus in the first one. Okay, chlorine, from your common ion chart, has what charge? What's chloride? -1, okay? And I have 3 of them, so that would be -3. That means phosphorus is going to have to be a +3. Okay, its oxidation number is going to have to be a +3. So that's why I put phosphorus 3 chloride. In the next one, I have a -5 because I have 5 -1s, so that has to be a +5. So I have to put phosphorus 5, Roman numeral 5, chloride. So are you getting how that pattern works? So the stock naming system on here is a little bit harder to do than just prefixes. And prefixes are easy to write the formula and even name them. Stock naming system on some of these actually gets a little bit harder. Now, if it was all metals, it's not, because you already have them memorized on your common ion chart. So, any questions that you have? That takes us to the end of this section. Okay, so here is our new assignment.